All right, so it's very exciting to be here. Thank you all for coming. And since I have the first talk, I will give some background material which might be well known to many of you, but I figured since it's the first talk, I might as well try to set the stage a little bit and sort of err to the side of having more rather than less introduction. So the motivation largely for my talk and also for this workshop is quantum simulation. It's the fact that we're interested in many-body quantum systems because we can that way predict properties of materials and molecules, chemical systems that are important for various applications. And not only molecular side, but also condensed matter side, where we have periodic systems. A large part of my talk will focus on molecular systems as examples, but I will also talk about a bit near the end about more on the condensed matter side. And of course, the reason we cannot tackle these problems classically is that the size of the Hilbert space grows exponentially with the number of electrons or qubits. And if we look at how many qubits we can simulate and how much memory we need to store quantum states, you see how quickly this explodes. And even in principle, when our memory keeps growing, we cannot exactly tackle more than some tens of electrons or qubits. And of course, the idea is to use quantum systems that we can control well to simulate other quantum systems. So we start from something that nature or a lab has given us, a quantum system on the left-hand side shown here that has strong correlations. We somehow map it on a quantum computer, and then we control the system on the right, and we make measurements on it to get properties out. So if we sort of step back and see what kind of equations are we simulating, we start from some fermionic Hamiltonian. In the top row, it's written in first quantization, where we have kinetic energy and Coulomb interactions. And it's the Coulomb interactions that make these strongly correlated systems and hard to solve. And typically, the first step we take, which might not be necessary, you can also think about solving things in first quantization, but I would say the large majority of the field first takes this classical pre-processing step, where we choose some basis. And if you think about a molecule constituting of atoms, you can think of the atomic orbitals as the basis, or you can think of first creating molecular states and using that as a basis. And there's a lot of wisdom of decades of work that's going into choosing this basis and picking it in the right way to make this Hamiltonian have a nice form. And here the H, these H's with the subscripts are scalars. They correspond to the integrals that you do in this particular basis that you chose of the first quantized form above. And then the A's, dagger A's, are operators that create or destroy particles in specific orbitals. And so these indices of the A's denote orbitals. And I'll use the word orbital to mean spin orbital, such that each orbital can be either occupied or unoccupied because these are fermions, and they have to follow Pauli exclusion principle. And the consequence of Pauli exclusion principle is translated into the operators in the bottom line, where you see that these anti-commutation relations hold. All right, so this is everything up to here is classical, right? We've done this classical pre-processing step, and now we have a Hamiltonian given to us in the middle in this box. Now, if I look at what the state looks like, we start from something that's explicitly antisymmetric that you see on the left-hand side in some bases that I wrote it down here. But now, since each orbital can have either 1 or 0 electrons in it, everything, if I translate to the second quantized picture, will look like a binary string. Right? So the first orbital in this case does not have an electron in it, so it'll be state 0. The second one has an electron in it, state 1, etc. And this is a very natural way to think about now translate into a quantum computer because we already have this sense of binary, a vector of zeros or ones. So this is the most natural way to map to a quantum computer. It's not the only way. I'm not going to talk about other mappings, but that's an active area of research as well. But let's just take this straightforward mapping where we associate, so we map orbitals to qubits. An unoccupied orbital, let's say the jth orbital, will be mapped to the jth qubit. And if it's unoccupied, I'll have that qubit in state 0. If it's occupied, the qubit will be in state 1, right, as shown over here. But of course, we're not done because our qubits, at least in this idealized form, are distinguishable. Right? They're well-defined and well-defined positions. There's no sense in which I have to anti-symmetrize their wave function. But the fermions are indistinguishable. So we have to also worry about that. Mathematically, what that means, I have to worry about the fact that the fermionic operators satisfy these anti-commutation relations. Whereas if I just look at individual qubits and I act with a raising or lowering operator, that doesn't care about other qubits, right? So somehow we have to go and impose that. And the way we impose it is we make that particular qubit care about the state of the qubits that are labeled below it, which we can do by adding these z operators, sigma z, or Pauli z's, as a tensor product. So the thing I have here is a product. I hope mathematicians are not upset. I mean a tensor product. And you can see that this index j is smaller than I, right? Because if I act with one of these, I have to worry about are the orbitals labeled below that occupied or unoccupied. So now by not just having raising or lowering operator in the particular qubit, but also these z's on the other qubits, I can now satisfy the anti-commutation relations that the a's satisfy, and I can have now an equivalence between my fermions and my qubits. All right, so this is the first step. So far, we have not done any simulation. All we've done is a mapping between the fermionic problem we're interested in solving and the qubits. So now we can go, of course, to the next step and say, what do we do to actually do the simulation? OK, so what's the objective here, right? I need to create the state of interest. Oftentimes, it's the ground state of the Hamiltonian I started off to simulate, or some low excited states. And then I need to, what I'm interested in is to measure some properties, right? It could be the total energy. If this is, let's say, a molecule where I can define it unambiguously. It could be some correlation function, response to electromagnetic fields, etc. And for this to be meaningful, it should be done accurately enough and better than classical approaches, which, of course, we're nowhere near yet, right? But that's the goal. So how would we do that? I already alluded to digital simulation, but I want to make this distinction from analog quantum simulation. This question sometimes comes up, especially later when I talk about pulse level control. So just to make it very clear, what's the distinction between analog and digital quantum computation? In an analog computation, you're essentially emulating the dynamics of the system you're interested in by recreating the Hamiltonian on the system that you're controlling, your quantum computer. So in analog quantum simulation, the native Hamiltonian of your quantum device coincides up to this mapping with the Hamiltonian that your molecule or your many-body system you start off with. And then you can, you have more control over the quantum system, however, so you can tune parameters and study regimes that in a naturally occurring system you might not be able to do. In a digital quantum simulation, the Hamiltonian you're simulating or measuring, etc., is not a native Hamiltonian. It is an operator. So the Hamiltonian that you're interested in the digital context doesn't really have a relation natively to the quantum processor you have, right? And in principle, you can solve any problem because now you'll have digital quantum gates, which I'll talk about in a moment, and you're not limited by what the native interaction is. of course, you need enough controllability in your quantum processor to be able to realize the evolutions you want.
So can I ask a question?
Yeah.
Maybe it'll help others to help me. Sure. Go back to that slide when you, so somehow you have your creation annihilation operators, which is in the Hamiltonian, and now you have these xi's and yi's, which is the language of qubits, right? Mm-hmm. This seems to be like really the fundamental mapping here, right? This whole business.
Yes.
I don't understand that. If you could repeat it once more, that'd be great.
Sure. So what you want, right? Let's go back here.
All that I understand. What I don't. Oh, okay.
Let me just in case. All right. So the question was about the mapping between fermions and qubits. So if we look here in the bottom row, right? These are fermionic operators. So they satisfy these anti-commutation relations. Yeah. Now, if I just go to qubits, and let's look at this line, the bottom line on the slide, and forget about the z for a moment. Just look at xi plus iyi. That operator takes you from 0 to 1 in your qubit, but it does not know anything about the other qubits. So if I were to take the anti-commutator or any commutator between this term and a similar term in another qubit, I would just get 0 because everything commutes. Right, so it wouldn't know, and that's because the qubits are distinguishable. But by adding these z operators that act on other qubits, then I'm forcing it to have the same anti-commutation relation as the a's I started off with. Does that answer the question?
Yeah.
So I'm making basically something that looks like a single body operator on the fermionic side, where all these things are built in. I'm forcing this to have the same properties by making it a many-body operator, explicitly. Yeah?
So, but then it's like it doesn't do the exact same, doesn't have the exact same effect on the system, but it's just similar insofar as it satisfies the same commutation relations, or is it more
It has the same effect on the system because I'm mapping everything.
Okay.
So you can go back, and everything should be consistent.
Okay.
Yeah, and feel free to interrupt me with questions. I should also give you a second disclaimer that I arrived from Sydney yesterday. So if I'm not fully coherent, it's probably, if I don't make full sense, it's probably not your fault, it's mine. So feel free to stop me and ask questions. All right. Okay. So yeah. So going back here, so I'll mention a few general quantum algorithms that I will not be focusing on, just as a motivation on why we're doing the things we're doing in the near term. So, all right, so we've done this mapping, right? But now we're not done, because what we want is to find a way to calculate properties of the system we're interested in. So let's give ourselves the simplest possible task to begin with, which is to find the eigenenergy of a particular of the ground state of a particular Hamiltonian that we're interested in. And when I take my Hamiltonian and map it onto qubits, there's going to be a lot of terms in it that touch different sets of qubits. And that's what this H total is. So what I need qubits to encode this eigenstate. And I also need additional qubits, which are sometimes called ancilla or auxiliary qubits, that'll help me extract properties. So basically, what this algorithm, this is kind of the prototypical quantum algorithm for quantum simulation. There's been a lot of more recent progress, but let's just take this because it suffices for all the points I want to make. So you start, and by the way, the symbol might not be familiar to everyone. The /n means this is an n qubit state. Even though I have one line, really, you should think of it as n lines, n wires. So somehow I start with my the state I want, I'm interested in. We'll get back to that. And what I want is to extract the energy. So how this algorithm works is I apply a conditional U operation, and U is just the evolution operator for that Hamiltonian for some time t that I've shown in the line above. And then by having put these auxiliary qubits in some superposition state and acting conditionally with this U, what happens is because this psi is assumed to be an eigenstate of the Hamiltonian, it's also an eigenstate of U. So when I apply this operator, I get out the eigenvalue, right? Because psi is an eigenstate. And then that is mapped onto the auxiliary qubits. And then I make measurements on my auxiliary qubits. This might also be a bunch of qubits here. So by repeating this experiment multiple times, I'm able to extract essentially the energy, the different digit of the energy E. Now, there's some subtleties with this. One is that this conditional U operator is a very nasty thing because I have this many-body Hamiltonian with many, many terms, and many have long strings of Pauli operators. And then I want to exponentiate it. So we do something that I'm sure the audience is familiar with called trotterization, where I take an operator and I chop it up in small pieces. And because these small pieces don't commute, I need to repeat this over and over. And when n goes to infinity, this is exact. In reality, we stop it somewhere and we incur some error. Now, this is really a difficult thing for existing quantum processors. I think most of the examples I know, they've stopped at first order. So here you're essentially pretending these things are commuting, then they don't. And there's also a lot of ambiguity if you stop at first order, because then you have to worry about how you're ordering these things, right? At the infinite limit, you shouldn't care, but at finite order, that matters. So another thing to point out here, okay, this I already told you, is that there's a big assumption here that this initial state, psi, is somehow created, right? But I haven't told you how to create it. So this is something that these algorithms don't really tell you how to do, right? The phase estimation algorithm tells you if you have a state that is the eigenstate you're interested in, then you can do this. In practice, it suffices if the state has enough overlap with your target state, and then the measurement will collapse it. And if the overlap is large, you have a high probability of collapsing to the state you want, right? But this is something that's not inside the algorithm. That step you've already somehow done. There's more modern versions of how to do this type of thing, some called linear combination of inters that I'm not going to talk about. We can discuss it offline. But the point here is that, again, this initial state is somehow assumed to be created in this case as well. So the reason I'm presenting these two approaches is to contrast them to what most of the community is doing now, because these are not yet doable. These control U's are really, really deep circuits that we cannot implement well in our existing processors. So to deal with this problem, we're trying to do something easier. And when I say easier, I mean something that puts less demands on the quantum processor, which is the thing that's not developed yet. The most sort of well-known such approach is called variational quantum eigensolver. And the idea here is that you want to leverage your classical computer in conjunction with your quantum computer in order to extract the types of properties you want from your many-body system. So the first step is the same. You still do the same mapping from the Hamiltonian to the qubits. But now this algorithm actually tells you also how to prepare the state. So there's, yeah, questions?
This is referring to the page before. So when you say preparing these long products is complicated, for small t, there's also something like Q-drift. Have you heard of that?
Yes.
That works too, right?
It works, but you still have to repeat. You still have to repeat.
You have to iterate up to a certain end time. But
yes.
The gates are sort of easier, right?
I mean, they're easier, but they still have the same components as the, yeah. So even that is not, it has some nicer sort of behavior in terms of errors, but it's still not, we're not there where we can implement it. Yeah, so the variational eigensolver relies on something called the variational principle in quantum mechanics. This is something that's well known in quantum mechanics. It's an undergraduate quantum textbooks. And typically it's taught after perturbation theory, where you try to somehow find approximate states, ground states of Hamiltonians. And it's a one-line proof that if I take a quantum state and I parameterize it in some way, no matter how I change these parameters, the mean value of the energy is bounded from below by the ground state energy. So what that means is I can take a parameterized quantum state, I can change parameters, and I can keep hopefully lowering and lowering the energy until I cannot go any lower. And if my parameterized state is parameterized well, which I'll talk about quite a bit in this talk, then hopefully when I cannot minimize anymore, I will have hit the real ground state. Right? There's no guarantee that you'll do that. So you'll probably have to search around a little bit, convince yourself you're not trapped somewhere in a local minimum. We'll get into all these things. But the idea here is that I'm using the quantum computer only to do the difficult part that I cannot do on my classical computer, which is store the quantum state. Right? So even in our noisy devices, we can still have many qubits. And hopefully, we can create quantum states of interest. And then our circuits, the depth of our circuit is such that I can actually create the quantum state I'm interested in. And then to extract properties, we're measuring. We're not using ancillary qubits to do conditional operations, which is the difficult thing at this point for our quantum devices. So how would this look like? I'm creating my parameterized state. So I have this theta, vector theta, which is just parameters. I'm taking the parameters that enter in this u of theta, which is a unitary operator. And I have this layer of u's. Each carries its own parameter or set of parameters. And then if I'm smart about how I have parameterized the circuit, then for some value of the thetas, I'm hitting the state. I'm creating the state I want. Right? That's the idea. And then I can go on the state and make measurements. I make the measurements on the quantum computer. I feed these measurements in the classical computer, where I perform optimization. And then I go back and I continue this process. And I stop when I'm convinced that I found the ground state. So let's just look at one example of such circuits. Here, you have single qubit gates and 2 qubit gates. In this particular example, all the single qubit gates are parameterized, and the 2 qubit gates are not. Right? You can do more general things. And I believe this is from an IBM paper. I should have put a reference. All right, so the remainder of the talk. So I had quite a bit of introduction, so I probably won't make it to everything I had prepared, but I'm happy. I'll be here all week. I'm happy to talk with people about things I won't get to. So I'll talk about what different ansatz have been used. And when I say ansatz, I mean this state preparation circuit. What are their issues? Then I'll start talking about the approach we introduced, which is adaptive quantum simulation. And if I have time, I'll talk also about a similar but a little bit distinct technique of controlling pulses. So this early paper, this was actually, first author here is Abhinav, who I think is giving a talk later today. This was actually the paper that I found very exciting and kind of got me interested in the field. Where they showed some variational quantum simulation of reasonable molecules. Meaning, these are, of course, things you can do on your laptop, but they're still non-trivial enough that, for someone who was in the field for a long time, before people could do a single Rabi oscillation experimentally, the fact that you could do this on a quantum computer, I found that very, very exciting and maybe somewhat surprising at the time. So as I mentioned, the ansatz they used was parameterizing single qubit gates. And then they used the C0 or C0-like gates that do not carry parameters between their qubits. And they just layered this. So they started from these parameterized single qubit gates. They had a layer of entangling gates, another layer of single qubit gates, etc. All the parameters carried by single qubit gates. And then you basically have to go and optimize these thetas. Now, what is nice about this, and this was dubbed hardware-efficient ansatz, as the name suggests, you're using interactions that are native or easy to implement on your quantum processor. So in that sense, it's a nice ansatz because you're giving an easy time, so to speak, to your quantum processor. But there can be issues with it. One is that it doesn't know anything about the problem you're trying to solve. So no matter what you're solving, you have the same ansatz. It's very generic. And so you don't have any reason to believe that this is a good ansatz, right? For example, there might be symmetries in your problem, which, usually or all the time there are, right? There's fixed number of particles in many cases. There might be a particular spin. There's many physical properties that your quantum system carries, which ansatz like this know nothing about, right? This is something very generic. From optimization point of view, there's a bunch of papers that showed that this is a difficult to optimize ansatz. Now, another possibility and another ansatz that have been used is something called UCC, unitary coupled cluster. And this takes inspiration from classical methods. And because of that, it does have some symmetries. So it's closer to the physical system you're trying to implement, to simulate. And the way it works is you have the fermionic operators in the exponent. If you can read this, I know this is small, but you have exponentials of A dagger A's and A dagger AA, etc. And this really looks like the sum. If you look at this term over here, it looks like the exponential of sum of such terms, such that this is a unitary operator. And each of these A dagger A, etc., carry their own parameter. Okay, so this in some sense, it's nice because it generalizes classical simulations. But now you have to deal with a few things. These are long, when you translate them to qubits, they're long operators. And also you have to trotterize again. So you have to worry about how do you break up this long sum in the exponent into product, right? And as I alluded to before, when you stop at low order, which you have to in existing quantum processors, then this can become ambiguous, which we showed that you can get different things in the optimization depending on how you trotterize. All right, so just to summarize, you can have two long circuits with these approaches. In general, you are not problem tailoring your ansatz, and there could be trainability issues. So this is like, in a nutshell, the issues you might have with this existing ansatz and the things we're trying to overcome. So what we proposed, and this is collaboration with Nick Mayhall, who's here, and Ed Barnes from Virginia Tech, is don't start from a fixed ansatz. Instead, create your ansatz as you go with the help of the quantum processor. So because your quantum resources are precious, meaning your circuit depth should not be too long, just add as many operators as you need. And that will be problem tailored by construction because you're growing your ansatz depending on the outcomes of measurements you're making on your quantum computer with respect to the Hamiltonian you're interested in. So schematically, it'll look like this. You start off with something very shallow, just one unitary operator. And then you add another one, etc. And you see these still carry optimization parameters, so you also optimize as you go along. I'll make this more precise in a moment. But the idea here is that you don't only vary and optimize the parameters, you also vary the circuit itself. Right? So it's a very, very simple idea. So the question is, how do you actually implement this? Right? So this is a general idea. Now you can legitimately ask, how do I know what these U's are or should be? Right? How do I select them, and in what order do I append them? So the first thing I have to sort of tell you, or you have to give me, is what are the possibilities for these U's? So these U's are unitaries. So they're the exponentials of an anti-Hermitian operator. Shown here is A sub m. And this is a part that's a user-defined part. So if you have your favorite quantum processor, it's good at implementing certain gates. You can give me those gates as the candidate gates to enter and create the quantum state. But this is not this is a part of the algorithm that's a user input, right? What are your possible operators? The next thing, once there's a pool of operators that I can choose from, is how do I decide how to append them? So the criterion we proposed, and you can have many different ways of doing this, but arguably the sort of the most intuitive thing you can think about is to look at, so you're at some point, let's say you're in the beginning or some point where you're running your algorithm, so you have some reference state size 0. And then you could add any one of these A's, right? So now I'm saying, okay, let's say I add A sub j, that operator, with its own optimization parameter theta sub j. I can look at the derivative or the gradient of the total energy if I were to add this operator with respect to theta and say I want this thing to be maximum, which means I want to add the operator that has the capability of changing the mean value of the energy the most. Basically, the operator that can have the strongest effect. And you can work out that this is just the mean value of the commutator with that operator of the Hamiltonian. And what is nice about this is that this now constitutes a new Hermitian operator, which you can itself measure it on the hardware. So you can think about actually doing this step on the quantum hardware as you go along. So now let me show you just the big picture, how putting all this together. What is your user input? It's the Hamiltonian you want to simulate, of course. The initial state, which can be some simple reference state that you can easily create on your hardware, and the operator pool, all the possible unitaries you can append to your circuit. So you take this state, which is either your initial state or if you're somewhere in the loop, the last optimal state. And then for each of these operators in the pool, you measure the derivative of the objective function like I showed you before. And then you select the one that has the largest derivative, unless they're all 0, in which case you just terminate. You select the one that has the largest derivative, and you, of course, exponentiate that and append it in your circuit, right? So that's the last operator to enter your circuit. And now you have a new optimization parameter, but you also have optimization parameters for everything that has been added up to that point. And you go and you re-optimize all these parameters. And an important thing here that I'll come back to in a few minutes is that you start your optimization from the previously optimized values of the existing parameters. Yeah, question? You're optimizing them all at the same time, but there's different ways you can do it. So those are chosen by how you have grown your circuit up to then, right? So let me maybe go back here. Right, so each operator I'm adding, right, have this operator pool. I have it in the next slide, here, right? So here I'm adding one operator through the gradient criterion. And then I'm exponentiating that with a parameter, and I'm optimizing that. So this creates a state. And then I add a second parameter by adding a second operator. And now I re-optimize both of these. Does that answer the question?
Yeah, thank
you. Yeah.
So can you go to the next slide?
Yeah.
Or a couple of slides, sorry, where you chose the optimization loop.
Yes. Yeah.
So you said you select the operator with the largest derivative, right? Mm-hmm. But shouldn't that be over, do you decide this largest derivative over all possible thetas? Like, how does that work?
So you're doing it with respect to previously optimized values, right? There are some follow-up works to ours that show that if you vary that, you could hit some lower minimum, but then it becomes a very, right, then we're trying to avoid making this an exponentially difficult problem, right? So you don't want to search over everything. So you are searching locally over what you've optimized up to that point. And I'll show you some plots that are, you can argue this is a good strategy. Yeah. Was there another question? Yeah.
When you say optimize, I mean it's already got to a local minimum, like for those parameters.
Yes. Local or global, we don't know. Yes.
Okay. Okay, so you're adding new operators is something like you try to get out the local minimum, or like?
So now you have a different objective function because you've added a new operator, right? So, let's say without this, I have an objective function. I optimize that. Now I add this operator. Now I have a new objective function, which in some sense is close to my previous objective function, right? I mean, that's a little bit of a heuristic assumption, but it's not crazy because I'm starting this at 0 and the previous ones at where they were optimized. Yes?
Do you use a kind of rank reduction method to simplify the operators that you get? Because I guess that if you apply repeated commutators with the Hamiltonian, the rank of the operator will increase by a lot.
You mean to approximate that with something?
Yeah.
We have not done it for all the simulations we've done, but you can. You could add some.
But you don't have to.
I think that's not your biggest issue with doing these things. Yes. Yeah.
So I think from layer-wise, like this reminds me a bit of layer-wise learning. And I think some things we noticed there is that it's better to not optimize the parameter theta1 until we really reach the minimum and then add theta2. So do you just minimize a bit, or do you really minimize this?
We minimize fully. We have not. I think there's a lot of room to follow up on the optimization aspect of this algorithm. To do things like that. You could think of layer-wise learning as sort of a special case of this, where you already know the use, right? And you're adding them. You're not selecting them on the fly. So any maybe conclusions that you have from that study could apply here, but we have not done that. Yeah, questions?
So in a sense, you're doing that in a greedy way at the beginning, and then, but when you are adding new, as you mentioned, you start with the set of parameters that you optimized previously, which may not be in an optimal
Exactly, you may
choice.
not.
So you may think about that different ways, but when you have the set of operators, you're working on a dictionary in a sense, like you have some set, and are there people trying to use maybe some techniques also from like learning, when you have, what is the optimal subset from the dictionary that you have available and so on, because there may be different ways how to do the choices instead of being like, standard grid.
I don't know of any ways that are not scaling exponentially.
Okay.
But there might be, from the machine learning community. That I don't know. But there is a follow-up to our work where they are just, optimizing everything. And then, of course, it's a discrete optimization that scales exponentially. So we do not want to do that. But I have a plot that might sort of answer some of the questions regarding optimization. OK. No more questions? All right. Okay, and just one remark here is that this, if you look at the quantity on the right, this becomes 0 when you hit an eigenstate, right? So nothing in this algorithm guarantees you that you're actually hitting the ground state, but you are hitting an eigenstate, right? So in practice, all our classical simulations, which that's all we've done so far, we have not run this on hardware. In practice, we always can find the ground state, and there could be things you can do to guarantee that, or to at least increase the probability of that. But the formulation of the algorithm that I described finds eigenstates, not necessarily the ground state. All right, so let me show you some early results before. Okay, I'm going very, very slow, but I prefer to answer questions instead of covering everything. So I'll be here all week, and whatever I don't cover, I can always discuss it with you. So these are classical simulations from the early paper on this. It's several years now. But let me just go through maybe at a high level, just to show you the performance. So here we compared different versions of the ADAPT algorithm. As I mentioned, there's this threshold, right? You stop when your derivative, your gradients, become 0. In practice, they become small, not 0. So you have to decide a cutoff, right? So when your gradients are below a certain point, you just stop. And you can set that gradient to be something small. And of course, as you make this number smaller and smaller, you should get better and better results because you have the same ansatz plus more operators. So here we're comparing these 3 different versions, corresponding to 3 different thresholds for 3 different molecules. Let's just look at one. We don't have to look at all of them. We can focus on the left column. Not surprisingly, you see that as I tighten the threshold, right, as I go to epsilon 3, I lower the energy. So in the x-axis here, we have interatomic distance. In the y-axis in the top row, we have the error in a log plot of the exact solution. This is something you can solve exactly. And you see that if I tighten the threshold, I get lower and lower energy. Very not surprising. It would be alarming if that didn't happen. And then we can compare to UCCSD, this ansatz I mentioned. And here we use the same operators that appear in the exponent of UCCSD. So you could think of this like some way of trotterizing UCCSD. And you see that you can do better than UCCSD in the top panel by going lower. The orange one is UCCSD. But now what's more interesting is that if I look at how many optimization parameters I have, UCCSD is a fixed ansatz. It has like 8 DAG arrays, a fixed set of them with each their own optimization parameter. So in this case, it's 60-something. But now you see that the ADAPT strategy requires much fewer optimization parameters to actually do better in most cases. Right? So this tells you that the UCCSD ansatz is actually unnecessarily complicated for these problems. But you wouldn't know that when you start off a simulation, right? What's nice about this algorithm is that you check as you go, right? You see how much the energy is lowered as you go along, and you can just terminate it when your threshold is satisfied. Yes, yes, okay. Maybe we can go.
All right. I got one question. So this is the case when you consider this specific example. So do you have any information for when people trying to scale up, say maybe arbitrary n qubit state or arbitrary n particle?
Maybe what?
Arbitrary n particle system, and what's the parameter number for UCCSE and the adaptive VQE? Instead of one specific example.
So for ADAPT, it's not a fixed number, right? Because you keep going until your threshold is satisfied, and you can see here, like you see here, right? As you tighten the threshold, of course, you need more. That increases. We can scale up and check classically, for small numbers. So I don't know how much that would tell us. But I mean, all the examples we've done, it always, in some sense, I'll show you one more plot in the next slide, but when you use the same operators, right, you have at least as much power as UCCSD has, and normally more.
Yeah, I guess the question is like, is the difference like a constant factor, or there's a scaling difference?
I mean, asymptotically, I don't know what we can do asymptotically, right? Because there's no, like, these are all heuristic algorithms. So, yeah.
So I have a question about when you look on the error plot, you have those kind of jumps, right? Are those exactly the points that correspond to where you kind of add additional, when the adaptive state happens, you add additional operator and then you have to re-optimize the accuracy?
So this is different Hamiltonians. As I change, as I move along this, this is a different Hamiltonian.
Because when you look on the other one, they look pretty smooth. So I was wondering why this particular, or maybe it's just an artifact from the plotting. Okay.
CCSD is known to perform poorly when the system has non-dynamical correlation. Does UCCSD have the same limitation? Yeah. So this is why you don't get so good results with UCCSD. Is that right?
I don't know if maybe I don't know if Nick has something. If you can say that.
Yeah, I mean, the correlations are limited to two-body interactions. So even though it's not going to be catastrophic in the sense of like kind of turning over like CCSD normally will, it still won't be able to describe that separation. In fact,
the next
UCCSD is worse. So.
Yeah, and I think the next slide might address a little bit your question. But is there one more question? Yeah.
So if I understood correctly, so these all like the ADAPT-VQE simulations are done using classical computers, right? So what techniques do you use for the parameter optimizations? And my next question is, as we can see, so for different bond lengths, you have different number of parameters in the ansatz, right? With my understanding, or just like an intuitive picture, with increasing bond length, I expect like there should be more number of parameters, but what decides or what is the going on behind different number of parameters behind for different bond lengths?
So I think
geometries?
I think that makes sense, right? You need more when you have more correlation, and I think that's roughly what you see. But if you compare, if you compare to each other different points, the common thing is the threshold. So you fix the threshold, and then the algorithm picks as many parameters and operators as it needs to satisfy that. Does that address?
I got the point that with different threshold parameters, we have like different like less number of parameters, but for different geometries, how to guess like a particular number of parameters will satisfy that particular geometry, because you see there are fluctuations. So for like bond 3 in LH, we have more parameters, but then you go at the end and
would you know that a priori? I don't think you would.
So
right? That's the nice thing about this, that you just run it and it tells you. You don't know that beforehand.
Okay. Yeah.
Yeah.
Do you have any result on the accuracy with respect to the choice of the set of the operators?
We have a lot of work. So you're asking how to choose the operator pool?
How large you should
Yes, we have a lot of that I probably won't get to, but I can just flash it and then we can maybe talk offline. But we have a lot of results. I mean, it's how you choose operator pool is very critical.
Let me spin up a question. If you don't choose the operator set sufficiently large enough, then you have necessarily the errors in your
let me give you the quick answer that sort of, covers a few slides that I'm not going to get to. So one thing we have shown is that you can get guaranteed, you can converge to a state, any state, with a linear number of pool operators in the number of qubits. Actually, the exact number is 2n minus 2. This is one of the few results we have that go beyond heuristics. But we cannot tell you how deep the circuit will be. So we can guarantee that operator pool that has certain features, which I don't think I'll get to, but we can talk about, yeah. And I think going back to your question about the correlations, one thing that you might argue is unfair in comparing UCCSD to these is that in these I pick operators like 8 dagger A's and 2-body operators from my pool, whereas in the other case, it's untrotterized. So you could argue, maybe when I start taking commutators of these, I would create higher body terms. So is it fair? Is it a fair comparison? So to address that, what we can do is we can take the same pool operators and just append them in a random order, and then optimize that ansatz and compare to how it does in this more sort of specific way of choosing operators according to the ADAPT criterion. And you can see that the energy in the y-axis, again, you have the energy error as a function of how many parameters you need. You go much faster with the ADAPT strategy to the ground state compared to other options. So this is non-UCCSD, it's trotterized versions of UCCSD, which I think maybe addresses what you're, All right, so let me make a remark about optimization now, which I think also came up as a question. So the ansatz that we get are systematically much shorter. That's what we set out to do, compared to fixed ansatz. So in this plot, and you can worry that if your ansatz is too short, you're not yet in this over-parameterized regime where you can reach, the global minimum. So you can worry about getting trapped in local minima or other sort of ugly parts of the optimization space. So what you can plot here is, as you move from left to right in the x-axis, you're running ADAPT and growing your ansatz. So here, for every slice here, I have a fixed form of the ansatz, the same operators. But what changes is where I initialize the parameters in my optimization. So the thing that's called here recycled initialization is the ADAPT strategy, right, of starting the operators from their previously optimized value. And that's the green curve. And you see that it does pretty well, right? It's not the global minimum, but it's a pretty good minimum, right? You're not getting sort of trapped all over here. But then if I start my operators at sort of random choices, then the landscape looks pretty bad. The algorithm stops, the optimization part of the algorithm stops, and these sort of, vary away from where you want to be. And the blue one is selecting the best initialization, which of course you wouldn't know beforehand, so this is not realistic, right? And this is just starting the parameters at 0, the red one, right? So you see the ADAPT strategy of selecting at the previously optimized value is about as good as you can get without having to search, unrealistically large values of the parameters. Yeah.
So except of reusing the parameter values, are you in your optimization algorithm, whatever it runs in the background, reusing any other information?
Yeah, that's something we're
Subspaces?
working on now.
Okay.
There's a paper that's about to come out on that, but I'd rather not say more just because it's the students' work, and I want to let her be the first one to talk about it publicly.
Okay.
Yeah, it's a very good question. Yes?
Assuming that you do VQE type measurements, the number of measurements you need to do to reach precision epsilon scales as 1 over epsilon squared, right? Say, for a given Hamiltonian sum, C over epsilon squared. So if you want to get the energy for a given Hamiltonian to precision epsilon, what is the scaling? Like, how does the number of measurement scales when you measure the commutators?
Yeah. It's a very good question.
I feel like this is an elephant in the room.
That's a very good question. So, okay, I think my time is running out, so I'll try to hit 2 slides out of my remaining 50 or whatever that address questions that have been asked. Okay, so this is one question, and I think there's another about the size of the operator pool. So let me skip a lot. You'll watch me skip now. So one type of operator pool we've looked at a lot is just Pauli operators. So instead of having a sum of operators like the UCCSD pool would have, the fermionic pool, these are just strings. It's much easier to say anything, to do any sort of analytical work with Pauli strings. So a lot of our analytical results are based on this pool. And the motivation for using these kind of operators is that they're simply the operators that appear if you do the fermionic pool and you drop the Z strings and you drop the sums. So you just take what appears, if you remember the slide where I had the Z strings, if I just were to drop those. So this is a pool we've worked on a lot. We have plots similar to the ones I showed you that you can see things work pretty well with this pool as well. Let me skip that. And let me just maybe make a remark on this, that you can define something called the complete pool, which I think goes back to your question, which tells you that when you take the full algebra, right, then you have a complete basis and you can get to any state. The pool itself can scale linearly, the number of qubits, but of course the things you generate are exponential, right? But you don't care because you don't do that step actively, right? The algorithm runs, it selects some operators, hopefully it stops at a point where you're not exponential, but there is this notion where you can have a criterion of is your pool complete or not. For Pauli pools, we have shown a few things. We have shown that you can have really nice looking operator pools, which are nearest neighbors, and only have weight 2 that are complete. So this is pretty hardware friendly. And another thing we've shown is that there's a nicely scaling criterion where you can check if someone gives you a pool of linear size to n-2, is it complete or not? And there's a criterion that scales polynomially that you can check this classically. One, because I'm talking to an audience of a lot of mathematicians, we have proven this in one direction but not in another. So this is an open question in our paper, and if anybody wants to look at it, we'll be very happy if someone proves it, but we're convinced about it, that this criterion holds. And in addition to that, you might not even need a full operator pool. You might not need your pool to be complete if you know the symmetries of your system. So you can restrict your pool even more by satisfying symmetries, and in some cases that even performs better than having the full pool. Let me,
Sorry, but
yeah.
my question, have you checked the Hessian of the your training? Not just the first derivative, but second derivative.
No, that's related, I think, to Agnieszka's question. That's something we've done, but we haven't published it yet. Yeah. So this is just an example that shows that in some cases, smaller pools perform better if you know how to smartly build in symmetries. There's another version of the ADAPT algorithm that we call Tetris ADAPT, where we, instead of adding one operator at a time, we add a few operators at a time. So we can compact our circuits more. I'm not going to talk about this, but I want to go back to the question about measurement overhead. So there's a very good question about the fact that in VQEs, you're already paying a pretty high measurement overhead. But now you have to also go and measure derivatives. So that way you're adding on, right, to your measurement budget, which is already quite high. So if you naively look at, and here I'm focusing on the Pauli pool, by the way, for which we have analytical results. If I just look at naively, I would sort of think, okay, I have all these terms now that I need to measure, right? If I take my Hamiltonian and my pool operators, and then I could think about grouping them in commuting sets so I can measure them simultaneously. That'll scale pretty bad. So that's not the way we want to go. Instead, if we have a Pauli pool, we can make the observation that if I have two commuting Pauli strings, then their commutators with a common Pauli string, with another Pauli string, commute. So this is something that's not difficult to prove. You can easily convince yourself it's true. So this sort of points us to the strategy of taking commutators of mutually commuting Pauli strings from our pool and measuring those commutators together. So what that means is, instead of grouping Hamiltonian terms like people usually do in VQE, we group pool operators together and then measure separately terms in the Hamiltonian. And you can show that for this particular Pauli pool we've been using a lot, it's quite easy to see how the commutation works and which terms commute, because they have this simple 1y and 3 x's or 3 y's and 1 x type of form. And basically what you can show, I'm not going to go into details, but it's on this paper, is that you can group together n to the cube operators, and that incurs a linear overhead. So you only need to measure linearly more. So this is a very encouraging thing compared to what you would naively expect. So is that a question?
I think I was going to say we should probably stop.
Yeah, I'll stop.
See if there's one question online.
Yeah.
We just got that.
Hey, thanks for a great talk. I was wondering, instead of measuring gradients, what if you tried like a gradient-free approach? Like, let's say, like a Powell coordinate search or Bayesian optimization, and then like you use one optimization step of that instead of taking a derivative.
So you're saying to use the operator that has the effect of minimizing the energy the most, like just actually look at the energy. Yeah. You could do that, and I think there's a few papers that have looked into that. We have some work that we haven't published where we've shown that it's not that different from doing our criterion. And it's more expensive because then you would have to also optimize at that stage, right? You would have to optimize for every operator.
Gotcha.
So we don't. It seems like you don't have to do that. Okay. All right. If there's no other questions, I'm skipping a lot. I just want to flash it just because I can discuss it if you want in any of the breaks. We have work on lattice models and a way to select pools for example, spin chains. We've done a lot of work also with Gibbs and open quantum systems. Let me just skip, sorry about that. And then we also have a way to do VQE by optimizing one layer down at the pulse level. So instead of optimizing sort of the digital gates, looking at the electromagnetic fields that produce these gates and parameterizing those directly, and have a similar strategy. Nick might or might not talk about this tomorrow. I don't know. Okay, but we're happy to talk about it in the breaks. So let me just not omit the slide. It's very important. So there's this great work, which I can say is great because it was mainly done by these young people and not by myself directly. And it was a very tight collaboration with Ed and Nick. And also, let me just advertise a little bit our new center at Virginia Tech. We have a really nice campus. We have an ongoing seminar series that we're happy to host people. So if any of you are interested in visiting us, let me or Nick know. And we have a lot of recent hires in many areas of quantum information. And we'd be happy to host anyone. Thank you.